Should I test 1/2? You could. Because it says at least one real zero is guaranteed. At least one, you could have two. It just so happens, though, what we did, we got a little smart doing this. And Chris, Jonathan, I think what we did then, now this was such a beautiful problem. We then took these remaining numbers and told what they meant. I didn't do any additional testing, you could though. Told what they meant. For example, guys, if 1/4 is a zero, which it is, I now have 3 of the 4 zeros that I need. One's missing. So those remaining numbers, the way I did this, guys, it started out with 4, 7, 62, 112, -32. That was for x to the 4th. As soon as I find one to work, which I did, I found 1/4. These numbers now drop this down to a what? A cubic?
Yeah.
So this says 4x cubed, if I know how to read these numbers, plus 8x squared, plus 64x, plus 128 is equal to 0. And sometimes this helps. I can go by grouping. And guys, in the first grouping, we'll take out a common factor of what? 4x squared, was it? X plus 2. And I think on the last one, they got a common factor of what? 64? Was it 64?
Yeah,
Yes.
it creates x plus 2, right?
I remember Chris said we could divide, but we could do everything by.
Oh, he did. In fact, exactly. I could have divided everything by 4 and help myself out more. Yeah, let me go and finish this up though. What we did. Take out x plus 2 there, leaving 4x squared plus 64 is equal to 0. That's by group. Split this up, look at this. There is another 0. -2. Which means when I add that to my list up here, we put on the side here. Now I have all 4 zeros. Just so happens, you say, Professor, how about this part here?
That's your plus or minus 4.
That's right. If I solve this, and this is where Chris suggested even earlier on to go ahead and divide by 4, which would help me here, and make this x squared plus 16, then solve it. Guys, when x squared is equal to a -16, take a square root, will be plus minus, and what's the best way to express square root -16?
Plus or minus 4.
Plus or minus 4i, and that takes you right back to the 2 we knew was there to begin with. Now, you talk about a knockout problem. I realize it's a Monday. I don't know how much you were thinking about this over the weekend. I don't know. Mr. Parker, were you thinking about something like this over the weekend?
All right.
Not quite. Okay. Yeah, most of us know. We have a life. Okay. Look at that. That is beautiful. Now, will the one that I've created for your quiz, for your exam on Friday, this beautiful? I'm trying to make it beautiful. And what will I do? I will give you steps here. I'll mention, please use intermediate value property, and I'll tell you what 2 numbers to test to see if there's an answer in between. So you don't have to worry about just randomly choosing 2 numbers. I'll give those numbers to you, and then you could go through and test. Okay, beautiful problem. Then Jonathan's telling me, Professor, after all that, they then said, please go back and put this original function in factored form, knowing those zeros. And we wrote this as, help me out, Jonathan, x plus 4i, was it?
Yeah, x minus 4i.
X minus 4i. Now, hang on just a second. Because I got points but not do this last. Now let's get the -2 out of the way. X plus 2.
Would it be 4x minus 1?
It's gotta be.
Yeah.
Look at this. That's gotta be 4x minus 1. And the extra reason why, I have some students who said, Professor, why can I not write like that? Because we solve this, z equals 0, solve it, you get 1/4. But the reason is, when I multiply all this out in the green, the leading coefficient should be a 4. Which it would be in the green the way I have mine. Here, x times x times x times x, if I should have chosen this version, the 4 is lost. You just end up with x to the 4th for the first term. Now, if I retain my 4 here, x times x times x times 4x, gives me four x to the fourth, which originally was given to me. So don't write like this.
So in this case, we wouldn't put an A in front.
No, I'm gonna take a point out.
Coefficient.
You're talking about if you put what, x minus 1/4?
No, I'm just saying, sometimes when we don't know that leading coefficient, when we don't wanna do the, finding A, we just put A in front of it. But in this
Oh,
case,
right
we
here, right
wouldn't,
here.
right?
Absolutely, here, very good. You say squeeze in an A here. Okay, if it's not there. Yeah, you could. I'm not too concerned about that.
And then on an exam, would it be acceptable to write the x plus 4i x minus as x squared plus 16? Or do you want to
well,
with imaginaries?
Okay, now, if I use the word linear, I don't want a quadratic involved. If I say linear, I want all these to be linear, no x squared. So if I use the word linear, I want all my factors to be linear. Okay. I've got to make a copy of it, show you guys what I just received from Columbia University for their first calc test. One of my students sent me the copy. See what math looks like there. Calc 1. Okay. Guys, anything else here? Now this is beautiful. Now you know what maybe I will ask afterwards. What else could I ask here that I have not done after all this, and you feel so good that you got the zeros, you have it in factored form, you use the intermediate value property so nicely, Descartes' rule of signs could be used. Oh, by the way, the Descartes' rule of signs, guys, in the original black, there's only one sign change. What does that mean?
One positive.
There should be only one positive real zero of the four, and sure enough, right there it is. So now you can keep note of 1/4 is the only positive zero of the four. And Descartes' rule of signs tells you that. Okay, and you could go through and find the negative zeros, possible numbers. But what else can I ask before I left this?
Find it. Oh,
No. What else? I'm not gonna do it here.
graph it.
Graph it. It's like Professor, geez. I'm gonna go to the university one of these days. Yeah. Okay, now please graph this, and of course you won't graph it in this form here. You go through and find your end behavior, which you'll see on this review for the test on Friday. End behavior, and what, cross touch. What else did we talk about? End behavior, cross touch. Number one? X and Y intercepts, all that.
It's the horizontal asymptotes.
No, that's for rational.
Oh, yeah.
That's, these are
It's
polynomials.
just in behavior cross touch, right?
Okay. Yeah, we could cross touch and all that, we can do that. I'm not gonna graph this one, guys. Anna Park, please tell the class, is this a polynomial function? Are all polynomial functions continuous?
Yes.
What does that mean if I graph it?
Can't lift your pen.
Thank you. You cannot lift your pens. Continuous. There are no breaks. No holes. No breaks. No asymptotes. Not for a polynomial. They're all continuous. Nice, well-behaved graphs. Rational, discontinuous. Okay. Right? Okay. Guys, anything on this one? I thought it was so beautiful. Jonathan, we appreciate you.
Thanks, Abby.
Okay. Okay now?
Yeah, I guess it's just, the starting point is what drew me on.
And I'll lead you into it.
Okay.
Because you guys could be here all hour, 2 hours, whatever, how many hours it takes for a test. You could be here all that time just trying to figure out, where should I start, Professor? I'll get you started. I'll type up where to get you started and sort of lead you into the answers.
Yeah.
Okay? Okay, with that said, Leo.
Sorry, I came in a little late. How did you find negative 4i and then 4i?
That was given to me.
Oh,
This was given to me.
okay.
And then.
They said out of the 4 zeros, they gave you negative 4i, then automatically positive 4i is gonna be one also. Before I leave this though, Leo, good question. Suppose it looked like this. Just out of curiosity, suppose they said that was a 0. Then automatically what would be the other one?
Negative 4i minus 5.
Negative 4i minus 5. That complex conjugate theorem, they come in pairs. Negative 4 minus, just change the sign in between. They let it happen. Didn't happen here. Leo, that's where that came from.
Thank you.
There's a homework problem and they gave you 4i, okay? Guys, I looked through, now, when your instructor gets nervous, whew, and you see your instructor, look at this. This is how much I've done so far. So I can imagine my students with all this. And then all of a sudden I have this, and you're gonna really appreciate me doing this, I hope. This is gonna be the review for the test. Which you're gonna be lucking out because there's parts of this that will be on the quiz Wednesday. So I'll let you know which parts of this will be responsible for you on Wednesday, and then the entire thing front and back, and what sections it covers and all that. You guys appreciate this?
Yeah.
Yes.
Yeah.
Okay, and then you'll get to practice on this. I'll get this out to you today. Test is not until Friday. And Park and Anna have already said they're gonna help you out. Right?
Mhm.
Yeah, find them in the math lab or find them somewhere and they'll help you out. Okay, I'll get this to you here shortly, guys. Now, chapter 3, I'm trying to think. Yes, a question came up this morning also. Here we go. Professor, I'm still a little confused about this. Rational function. You know what it looks like? It's R of X is equal to P of X over Q of X. And I know Q of X cannot be 0. Now that's the one that's not behaved. This is one that has asymptotes, holes, crossover points, holes on the graph. It's a mess. Now, Chris was asking, Professor, can you remind me again, how can I find the horizontal asymptote if it has one? Quickly.
If the degrees are the same on the top and the bottom.
There you go. That's the one we're talking about. But there's 3 cases. Case 1, let me see if I can remember how I set this up. If your function looks like this, y is equal to, let's say, a x raised to the, oh boy, let's see how I label this, guys. So I will not throw this off. Oh, here it is. X raised to the m. And down here, b x raised to the n. Let's use those for my x parts. Case number 1, which is the best case ever. If the 2 exponents, they degree, numerator and denominator, are the same number. They match up exactly. Then the horizontal asymptote can be found right quickly by, and you guys probably know, by doing what?
A over B.
Yeah, y is equal to a over b, wherever that comes out to be. Those coefficients. And then we'll take the location of the horizontal line acting as an asymptote. On the other hand, if, I'm gonna call this case A. Case B, if, let's say, m is, I wrote this down so I will not mess it up. Beautiful. If m is equal to n plus 1, I think we're taking it like this. The one on top is exactly 1 larger than the one on the bottom.
It's an oblique.
That's where you have the oblique, and that's where that long division comes in and all that mess. Okay, so you will have an oblique asymptote. Now outside here, long division. Case 3, let me see. I had mine written up, I think, to take a look at the same thing here. If m is less than n, if m is less than n, then it looks like they wrote this, that you will have a horizontal asymptote. Does anyone think they know what happens if the top exponent is less than the one on the bottom.
0.
Well, automatically, horizontal asymptote will be the x-axis, y equals 0, which is the x-axis.
So if you have like x over x squared,
Exactly. Exactly. Okay? So I think those are the three we need to worry about. So when you examine this, guys, the rational functions, look at those exponents, please, the degrees. The best case ever, please, Professor, give me this one, is when they match up. It's merely A over B. You're done. And then the other two cases, this is the most awkward one because of long division. If the one on top is exactly one larger, you get a linear straight line called an oblique asymptote. If the one on top is less than, maybe a 2 up here and a 3 down here, you're going to end up with the x-axis. That's the end of horizontal asymptote. Here you go.
Doesn't case B and C?
So you gotta go, exactly. You say, wait, Professor, aren't these two sort of saying the same thing here? And your textbook says they are. You go, I pointed out two different pieces here. If it's exactly one larger, it's a special case for an oblique.
Oh, okay.
Beautiful. Well, the guy is on it. Absolutely. Okay? And those are the ones we talked about last week, you remember, in the long division. Some of you guys have forgotten long division, and whew, it was a mess. Yeah.
is there any chance that we could work through an oblique where
No,
we can
maybe.
use synthetic?
Hang on, let's see what I got
Can
here.
you, cause you can always use synthetic, right?
No,
No?
that came up in my 11:30 session this morning. I'll point out something here for you here. Let's see if I brought one in. Oh, I did. Oh, no, I didn't. Oh, yes, I did. You wanna see one with an oblique?
Yeah.
I think, okay, here we go. Let's sketch right quickly. Part B.
Oh, will this one be able to, we can do synthetic on this one, this particular one?
Okay, you got one there for me?
Or, I don't know, it was based on Chris's, earlier
Okay,
observation.
maybe we sketch it. I'd like to have a nice one though. Let me just create one here right quickly. Let's see, on top here you have, Eric, you're asking, I want the top exponent to be exactly one larger than the one on the bottom.
So like an x squared over
You want x squared on top? Okay, got that. That goes to x squared minus 4. And down here maybe what? X
X plus 3.
3, oh, that's okay. This one, guys? Is the one on top exactly one larger? Okay, so there should be an oblique asymptote. Also, I could simplify this somewhat, guys. This would factor, of course, the way I created this.
It's a difference of squares, right? So
It is a
x
difference
plus
of
2x
squares,
minus, or x
absolutely.
minus 2x plus 2.
Over that. I don't see anything canceling. Sometimes cancellation will take place, and what does that mean?
A whole.
That's a hole in the graph. We discussed all that last week. This one, no cancellation, so if I want to see a graph fairly quickly, then we'll show what that oblique looks like. Out of the way here. Guys, we do have an oblique asymptote on the side here for this. Let's do this. I'm going to use long division. You're dividing x plus 3 into x squared minus 4. Now, I better play it safe. I've got x squared minus 4. Is there a term missing? If you have it in descending order, I would expect maybe after x squared an x. So I'm gonna put a placeholder in there. So I got x plus 3 into this. Just to play it safe. Because the x was missing. Okay? Now, how's that long division always start? After we set it up, you always ask yourself, how many times will the first term go into first term?
Twice.
So x into x squared is like you on the side saying he wants the answer for this, which is merely x. That's a start. Now, after you get a start, you multiply this in the green times the divisor, divisor out front, x plus 3. Distributive property would give me x squared plus what, guys, 3x? I think. The next step in long division always is, what am I ready to do now? Subtract, which means for us merely to change signs. X squared will cancel, which I thought they should, but I end up with a negative 3x here, bring down my next term, minus 4. Now start the process all over. How many times will the first term x go into now negative 3x? There you go, on the side you're thinking about this. X into a negative 3x in the blue there. X is canceled, you get what, negative 3? Now take that in the blue times the one out front, the divisor out front, so negative 3 times the x plus 3. Distributive property, negative 3x, what's that, minus 9? Change my signs for the last time. If there's no mistake, I have a remainder of 5. You guys agree? And that remainder is going to play no part for us. So Leo, this I have right here definitely is in the form of, way back, mx plus b. In other words, it's a line. Slope of 1, y-intercept negative 2. That's my oblique. Okay? So we got the oblique asymptote. Guys, let's graph this then. Let me put that oblique on there right now. If you guys want to use slope, y-intercept to graph it, go for it. I'm going to just quickly find the x and y-intercepts on it. If I set this equal to 0, I get a 3. So my x-intercept is out here at 3. And this is for the oblique, this is not the graph. The y-intercept, replace x by 0, I get a negative 3. Patient. Here, since I know this fairly quickly, guys, we'll have an oblique asymptote, something like that. We have to guide this graph. Yes or no? Now let's get the graph. The graph right quickly, guys, can anyone please look at this real quickly and tell me where are the x-intercepts, if any?
2 and negative 2.
2 and negative 2. Put those in green. So there's 1 and 2 here.
Wait, what about the vertical asymptote?
That way, hang on. And negative 2.
Yeah.
You got 2 and negative 2. Y-intercept. Look at that, positive 4/3. Is it positive 4/3? Replace the x by 0. Replace x by 0 to negative 4/3. Do I end up with a negative 4/3? Okay, so it's down here at negative 1 1/3. You guys, let's squeeze that in right there. A little bit below negative 1.
Is there a parabola?
Hang on. They get too excited about it. And now, where's the vertical asymptote? How do you find the vertical asymptote? You set that denominator equal to 0, you will get a negative 3. So it's over here, like this. There's your vertical. Guys, we've got the intercepts, we have the x and y intercepts, we have the oblique, we have the vertical. Now I need the graph. Now there should be something happening to the left of that vertical and something happening to the right. I just have one vertical asymptote. To the left, if I have no mistake, I don't have any points plotted. And I don't know whether we want to take a guess yet where the piece is. Right now I would think, well, Professor, okay, I don't see it right now. You guys see what's happening on the left? We can try. You
Maybe
think
plug
it's,
in
now,
negative 4.
keep in mind, this is the x-axis. This is not a horizontal asymptote. Is it true?
Yeah, Eric said we could plug, we plug.
I would, absolutely put in numbers, get an idea. Eric, out to the left of negative 3, I'm going to just quickly put in negative 5.
Negative 12.
Okay, you're trying there. Negative 5.
Negative 4.
Negative 5 will make this 25 minus 4 is what, 21? 21 over a negative 2. Did I do that right? Is it 21 over a negative 2?
Gives you a cleaner number if you plug in.
I get later, but is that negative 20, negative 10 point something? Is it negative 10 point something? So that means out here at negative 5, it's way down here.
Negative 10.5.
So something's going on. Whew. Maybe we should try to get the inside part first. or on the other side. The other side, you gotta pick up this, you gotta pick up that, you gotta pick up that. I heard Eric say, Lord, sort of like a parabolic graph, and follow those asymptotes. So I'm thinking, guys, let me put this in, the final graph, let's try black. And he thinks, and see if you guys will agree, Professor, I think it does this. Comes down, picks up that point, comes on down, picks up this y-intercept, comes back up, picks up this, and sort of follows that oblique on the other side. Guys, is that reasonable? Does it follow the oblique? Does it follow the vertical? And it picks up my points. So my problem is now, where is the graph on the other side? There's one piece missing. And we could try points. I think I tried -5 and got -10 point something, so it's way down there.
-4 is -12.
Oh, -4 plate in here?
I think so. 'Cause it's
Okay, I see 16 minus 4,
over
that's
-1.
12. Oh, -12, it is -12. So you could move out to a -4 and that drops down even further, what, -12? Oh, cute, where is it?
Below the x-axis. Or like-
Oh, it's gonna be below the x-axis, definitely.
But in terms of drawing.
Look at this, guys. Look at this. You see that oblique, what's it, oblique out? The oblique asymptote, let me extend it, I'm running out of board space. Extend it, is it down there? And is the vertical, if I extend it, it's down here? Is that true?
Yeah.
Guess where that last piece is?
It follows the oblique,
Oh, tell me more.
like numbers above the oblique following,
Now you mean up here doing this?
no, below the x-axis.
See, here you go, beautiful. First, you might think, well, Professor, could I draw it like this? Follow that green, vertical, and sweep down and follow the oblique, the blue. But what's wrong with that?
You cross the x-axis.
You're gonna cross the x-axis, and there's no x-intercept over there. Hugo says the best you can do then to follow those asymptotes, the green and the blue, it's squeezed in right here. I have put that in black. Ah, cute. It's down there.
Oh, that's pretty interesting.
It's down there. Does it, by the way, does that little piece follow those asymptotes? Does it follow the blue and the green? It's down there. That's why we were getting those strange numbers, -12, -10. Nice. Okay? Now, mine looks so small because I ran out of board space. But it's down there caught between, right here, little curve right here, guys. And then of course the other curve up here. And there's your example of a rational function with an oblique asymptote. Chris was concerned about that. Leo?
So oblique asymptotes have just 2 parts of the graph, while like,
Now, it depends on how many vertical asymptotes you have. If you have 2 vertical asymptotes, I just had one here, then there's something to the left, something in between, something to the right. It's 3 pieces.
depends on.
Okay, how's that look? Okay.
Oh, could we not have also just kind of assumed that would have followed the bottom asymptotes because there's no x-intercept that would
There you
pick
go.
it up on the left?
Exactly.
Okay, yeah, that was gonna be-
That's what you're thinking. I love that.
That was gonna be my next question.
Absolutely. Good. And not plot points. Guys, we okay now? Is that a good little recap?
Yeah.
of What's been going on?
Do oblique asymptotes have to work similarly where one will be on the right and one will be on the left? Like the way that a vertical asymptote works? Does that make sense?
Are you talking about the oblique or vertical?
Yeah, because in this case, the top part is on the left of it and the bottom part's on the right of it.
Yeah, you know, for the vertical.
No, for the oblique.
Oh, for the oblique, oh, you're surprised, it depends on how that oblique is drawn here, it's a straight line, of course. So you're saying there's something happening to the left and something happening to the right?
Yeah, and I think that's the case for the other one we did. as
Okay,
well.
okay, I see what you're saying,
Yeah, it is.
that's what you're saying. Hope you guys are reading this. Good recap?
Yeah.
Are you guys enjoying life? I'm really coming here, I don't know. Ooh. I don't know. Bart, and we may have to start having a little beach party or something on weekends. Or we still do math. A little party of some sort. I think on the weekend, they're not thinking too much about math. Uh-oh, okay. Now, I think it's a good recap.
Yeah.
Definitely a good recap. Now, guys, what I need to do, let me see if I'm ready. And I am telling you, we gotta get ready. Before I jump into something entirely new, here we go. Inverse functions. We discussed them. Okay, so I need to, now guys, please tell me, I hate to erase all this right now, it's so beautiful. If I did my inverse function example down here, I hope, can you guys in the back see that? If I put it down here? Okay.
Yeah.
So I have one right now, we need to talk about, and then we'll jump into the new stuff here. Okay, given. Given this function f of x is equal to 1 plus 3x over 5 subtract 2x. And on the side here, I said this function is this. It's 1 to 1. Find the inverse of this function, the domain of the inverse, the range of the inverse, and check it by showing this. There we go. By the way, guys, does a function have to be 1 to 1 to begin with in order to have an inverse?
Yes.
Okay, so if I don't point that out, you may say, Professor, you didn't point it out to me on the test. Okay, this one, it says it is 1 to 1, so that ensures there's an inverse. So let's find the inverse, find the domain of the inverse, range of the inverse, and looks like I want you to sort of check it by forming a composite, and hope you get X. If I don't get X, and you don't get X maybe on Wednesday, you got troubles. Okay, now does anyone recall, there's only 2 steps. What are the 2 steps, David, to find an inverse?
Equal it to y. Or equal to x, I mean.
In other
Replace
words,
all the x's
what's the
with
key word?
y's and set equal to x, right?
Well, what's the key word?
Replace all the x.
Interchange. Don't you interchange the X and the Y? Is that true? That's the essence of an inverse. So I'm gonna go back up, of course, that's a Y there on the left right now, so put an X, and in place of the Y's, X's for the Y. Just interchanging the X and the Y's. That's step 1. Can't go wrong, 2 steps. First, interchange the X and the Y. And then second step is solve for Y. That's the next step. Solve for Y. Guys, I'm gonna do a quick cross multiplication in step 1. Now 5x subtract 2xy. Gotta watch my algebra here. I'm thinking this x is x over 1, and of course in the other direction, 1 plus 3y. Look, quick cross multiplication. I want to solve for y. I see a couple terms with the y in them. I want those terms together. So I'm going to move things around and rewrite this as 5x subtract 1 and move the 2xy over. Let's turn things around. Why get those terms together? If I'm trying to solve for y, what am I going to do?
Factor out y.
Factor out that y. That's why I got those terms together. So this is 5x subtract 1, take out a common factor of y, and you have 3 plus 2x. Now keep in mind, we're trying to solve for y. To get the y completely by itself, divide both sides by 3 plus 2x. 3 plus 2x. These, of course, cancel. And this, I'll block it off. That's your inverse. If I have no mistake, watch out for signs. Mistake. There's your inverse. So we got that out of the way. That's done. I can make this a stronger statement. This is your inverse. That's a big part of it. Now I'd like to now express, with your help, the domain of this inverse. Anyone tell me what would you be looking at for the domain?
What can x not equal?
I've got 3 plus 2x in my denominator. So you're saying, Professor, be careful, you can never have that, to come out to be a 0 down there. So in your mind, you're saying, if this should happen, and solve it, and do not let me make a mistake here, x is equal to what, -3/2? Is that true? So that means x cannot be a -3/2. That would make it a 0 denominator. So guys, my domain here is, after I thought x cannot be -3/2. You guys would like integral notation? It will be written like this and this.
So, Professor Ramsey,
Yes.
you'll never ask us to use set notation, cause I haven't seen like any,
No.
like set notation.
No. You could. No.
Okay, but if I wrote it like in set notation,
You go for it.
would it be fine?
That'd be fine.
Okay, perfect.
That's it. With me, guys? So far, so good? Don't make a mistake here. Now, that's my domain. Now, the range of the inverse, we have no mistake, and Anna and Mark are watching. The range on this.
Just find the domain of the top.
Thank you, that's what I wanted to hear. You're saying, Professor, I cannot quite look at this. This is the inverse. To tell you the range, I can tell you the domain easily, but I can't tell you the range. So X says, oh my goodness, go back up to what was originally given. This, their domain, its domain range. Guys, up here, the domain on this one was X cannot be what number?
5/2.
5/2. Beautiful. The range on this one,
X cannot equal 3/2.
look at that, the range on that one, if I get stuck up there, should be the same as the domain on the inverse. And we just said the domain on the inverse is what? X cannot be that. So therefore, I know automatically Y cannot be, in this case, what was it, -3/2?
Yep.
That's being clever. I mean, super clever. Now, do we have enough now, since I mentioned the domain and range up there, do we have enough now to answer the range on this? And he says, yes. I'm gonna put this, guys. He said, Professor, that should be equivalent to the domain, since everything's being interchanged, the domain of the original. Which was, X cannot be 5/2. Yes or no? And since I'm looking for range, let's use a Y here. So on the side here, Y cannot be, and the number was back up here, 5/2. If you wanted interval notation or set notation, Jonathan, go for it. And it looks like that. Wow, wow. Can you guys keep all this straight? Leo. All right, close this down. This one, I guess I've just been here half an hour, got all this different stuff, that's beautiful. Leo, now be careful, I don't want to put you on the spot. Here's the original function. It's a rational function. I'm not gonna graph it. I could. Could you tell the class where, if I should graph this, where is my horizontal asymptote located for the original black function here?
-3/2.
I love it. -3/2. Does everyone see that? That's the domain, the horizontal asymptote on the original function. And we just had a discussion about the horizontal asymptote. The degree exponents are the same. So therefore, the answer should be, he gives to me -3, Professor, over a -2. Those are my coefficients. Just turn around a little bit. He says -3. Now that's my horizontal on the original. Guess what that turns into on the inverse? The vertical. That's what the inverse does. It switches everything. So now if I jump down to my vertical, my inverse, and ask you for the vertical, you know how to find the vertical asymptote. You set this to 0. X's cannot be what number here? -3/2. So you can find the horizontal on the original, which corresponds with the vertical on the inverse. Let me do one more thing here before I take questions here. Guys, can anyone tell me right quickly, where is the x-intercept on the original black function?
-1/3,
Negative 1/3.
which is, does that
You
become
set
the
that
y
equal to
intercept?
0 and solve it, 1 plus 3x is equal to 0, you solve it, you get what? Negative 1/3. Now that's the x-intercept on the original. What should that negative 1/3 be on the inverse? The y-intercept. Let me jump down to it. To find the y-intercept here, you replace all the x's by 0 on the inverse, you get negative 1/3. Where these drop out and leave you negative 1/3.
And then the y-intercept on this
Whoa,
one is.
whoa, I know, exactly. So I'm not gonna do anything else, but you could test more, yeah, absolutely. That makes you feel good, when you see those things are sure enough interchanging. That's what an inverse does. Okay. Now, after all that though, Jonathan, who knows, we're not perfect. It's this down here, all the algebra. When you move one thing to another side, and the sign changes, and sometimes you forget to change the sign, whatever, and you get the answer, and all of a sudden you get your quiz back and you got a 0. And you get offset. Professor got 0 out of 10, oh my lord. Here it is, the 4th week, and I can't do that. So what am I gonna do? I'm gonna ask you now, officially. Now let's just look at the horizontal turned into the vertical, vice versa. No, check it. Here's the way you check it. This is what they suggest in mathematics to check to see whether or not you found the right inverse. Find this composite, which the way I have mine written means take f of the inverse. I'm gonna show you what happens there. I'm gonna do it. After I do it, clean it up, it better come out to be merely x for an x. If not, I have the wrong inverse. Guys, this means, in this case, place inverse into the function. There's my inverse. That's the blue. You're placing that into the black. That's all you're doing. That's what that means. You're gonna color code this. So you guys are saying sometimes if I color code things, it helps. So guys, I'm gonna end up with 1 plus 3 times, this is in the black. And then in place of x, I'm gonna put the inverse, there's the blue. I'm gonna look messy. Looks like this. Close that up. And now the bottom part, denominator, I think it was a 5, wasn't it? Yeah, it was 5. 5, subtract 2 times, in place of x, down there, you're gonna put the inverse again, this. Looks like that. Close it up. I hope everything's marked clearly for you guys to see. That is an x right here. That's what it says to do, put the inverse into the original. Now, as much math as I've had, and I've told you guys many times, I've had a lot of math. You think I could just stand here and say, yeah, that's x? Professor, this mess, when you cleaned up, is x. I've got to do the work myself. I don't know whether it's x or not. But when I simplify this or clean it up, it better be x. Just mere x comes out. That's where you check these things. Eric.
Instead of going through this whole process, could we not just plug a random number into f of
No,
x? And
no.
then.
How many random numbers are there out
No,
there?
just, if we, and then when we get y, we plug y into the next one,
No.
and it should spit out our
You can do
x.
that all day, all your life. And all of a sudden, that way out there, sudden, maybe when you turn 100 years old, you're still doing it.
I thought inverse functions have this, like, when you, f of 1 would be just 3, so then f of 3 would be 1.
Oh, that's true. That's true. But you got test 4, you got test negative 10, you got test pi, you got test radical 2. No, you don't have time for that. I wish you did, but you don't have time. The infinite number of numbers, here's the way you test. Now, here it goes. This is my algebra involved here. Guys, on top there, I would suggest you put these two together. First, we'll clean it up a little bit. On the other side, I got 1 plus, what's this? 1 plus, if you want to think of this 3 as 3 over 1, and multiply those two together, you could. That would be 15x minus 3 over 3 plus 2x. Not bad. Let's jump down to the bottom here. Down here, you could, be careful, you could multiply those two together. See what that looks like. So I got a 5 out front. This is scaring me now. And if you multiply through by -2 here, guys, you're end up with a -10x plus 2. Help me out. Is that -10x plus 2? -10x plus 2. Oh, geez. Put a plus sign here. -10x plus 2